Dr. Rachael Livermore.
Thank you, number one. All right, so the science of Star Trek First Contact. Right at the beginning of the movie, we get this really nice shot of the Enterprise.
Stardate 50893.5. The moment I have dreaded for nearly 6 years has finally arrived. The Borg, our most lethal enemy, have begun an invasion of the Federation. And this time there may be no stopping them.
So, it's very pretty, but anytime a nebula appears on Star Trek, I have to have the same rant. Which is, these very, very pretty images are very similar to things you see in like glossy magazines from the Hubble Space Telescope, right? This is a big telescope that integrates for lots and lots of hours to get, well, minutes if it's close by, to get these really nice, pretty pictures. But nebulae, they're regions of very dense gas and dust where you might form new stars, but they're dense compared to a vacuum. So I've got to bring out my trusty plot. Those of you who've been to these before will have seen this plot. There is no such thing as empty space. What we call a vacuum of deep space has actually about an atom in every cubic centimeter or so. And as I said, nebulae are dense regions. These are regions that are collapsing under gravity to form stars, so they're denser than that. Quite a lot denser. This is a log plot, which, as I've said before, I would never normally put in a public talk, but in this case it's necessary. That means every one on this plot is a factor of 10. So a dense nebula can be 1,000,000 times more dense than empty space. Pretty dense, right? But not as dense as this thing, which is a quadrillion times denser than a dense nebula, and those of you who've seen this plot before know what this is. What is it? Air. So this very dense nebula is a quadrillion, that is 1 with 15 zeros, times less dense than air. Now when you're seeing it from a distance, you're seeing the accumulated effect of all of this density over some volume. If you're in the middle of it, it's not even going to look like a fog. So it's actually not going to look that pretty as a backdrop to your pretty spaceship, I'm sorry to say. Now, since I ranted about this 2 weeks ago at 2001 A Space Odyssey, I should also point out that the lighting on the ship is not quite right. The shadow on the I don't understand what's lit on the right side as we were looking at it. I don't know where that light is coming from. They're not in a solar system. There's no sun shining directly on them. But given that there is apparently some source of light, the other side of the ship should be completely black, not like a shadow you'd see on Earth because there's no air reflecting the light. And since I ranted about it in 2001, it's only fair that I give Star Trek the same treatment. But this scene, which comes shortly after this, actually annoys me even more.
What do you have? We finished our first sensor sweep of the neutral zone.
Oh, fascinating. 20 particles of space dust per cubic meter, 52 ultraviolet radiation spikes, and a Class 2 comet. Wow, this is certainly worthy of our attention.
So, please excuse my language, but fuck you, Picard. So, first of all, space dust, not boring. Space dust is really cool. This is an image of the entire sky taken by the Planck satellite. What you're looking at here is dust in the Milky Way. There is a lot of it. It's actually not that much, but you know, space is really big, so there's a lot. And what you're seeing here is, if you've seen projections of the Earth projected on this kind of oval shape, it's the same thing but the sky. So this is the entire sky seen in dust. And you can see this line across the middle, that's the plane of the Milky Way galaxy, which is a flat disk. Lots and lots of dust in the plane, and then some swirly bits above and below. There are people whose entire job is studying this dust, and I'm sure some of them would really love to be in a spaceship out there actually able to study in more detail than we can do here from Earth. And Picard is not appreciating this opportunity at all. The next thing he says is there's like 50 UV radiation spikes. This is also a thing people really study. This is the SWIFT satellite, which can observe in X-rays, ultraviolet, optical, and it looks at these flashes of UV radiation, what we call transient signals, which are usually from flaring stars. And these are really cool. To give you an example, this is an M-dwarf star. This is a star that's smaller than the Sun, so also known as a red dwarf. They're far more common than the Sun. They're smaller and they're cooler, and they tend to be quite active. And people study the flares on these stars. They're really cool. Here's the Sun for comparison. You can see that a red dwarf is much smaller than the Sun. This is an extract I took out of a video made by NASA. You can watch the whole video for explanations of what's going on. It's really cool. This is the biggest solar flare ever recorded on the Sun. It was recorded in 2003. And this is what's known as an X45. That's just the number they give to it. That's what it looks like. It's pretty cool. Stars are really cool. Those of you who saw the eclipse may have actually got a view of some of these things blowing off the Sun. They are very, very cool. But this M-dwarf is even cooler than that. This signal, which was received in 2014, would be, on solar scale, an X100,000. These are the brightest signals that you see flashing in the UV. They are very, very cool. Again, it is people's entire job to study these. And they, again, would love to get in a spaceship out closer to them so they can study them in more detail. The last thing he described was a Class 2 comet. I don't know what a Class 2 comet is. That's something that's been invented at some point in the next couple hundred years. But comets, as we know them, exist in the solar system. They can come from either the Kuiper belt in the outer solar system or the Oort cloud that surrounds the entire solar system. If you're seeing a comet out in interstellar space, we've never done that. That's pretty cool. Wouldn't it be cool to be in a spaceship where you can study these in lots of detail? So Picard really does not appreciate his job, is what I'm saying. Frankly, I would much rather look at these things than fight the Borg, but that's just me.
There she is.
Here we go.
Beautiful.
All right, take a look.
Well. What have we got here? I love a good peep show.
So again, here's one the amateur astronomers might appreciate. When you look at something in a telescope, it's not going to stay still because the Earth is rotating. So you have to have a clever motor attached to your telescope that counteracts the Earth's rotation and follows the object. However, the Enterprise you saw there was moving even within the field of view of the telescope. It is presumably not in geostationary orbit, which means it's not staying directly above one point of the Earth. If it was, it would look stationary. So it's going to be moving really, really fast. We don't know what orbit it's in. They do start saying the height of the orbit and they get as far as 3, but I don't know 3 what, 300, 3,000 meters, kilometers, who knows? So I don't know how fast they're going, but it's going to be fast. Because even a low Earth orbit, if you've ever watched the ISS pass overhead, goes really, really quickly. You're going to lose that in a telescope field of view in the time it takes Geordie to usher Zephram over to come look at it. So I have no idea what kind of crazy tracking device they have on that telescope, but I'm sure lots of people in this audience would like to get their hands on it.
Well, I sure as hell am not going up there sober.
What is that?
That is the constellation Leo.
No, that.
We already know the date because this is a really significant date in Star Trek history. It is the evening of April 4th, 2063. And they're walking outside here and they look up and they're looking at the constellation Leo. So far, so good. You can see Leo in April. Here's the night sky from Montana on April the 4th, 2063. For those of you who don't recognize constellations, here's some fancy artwork. You can make out Leo, the lion up here. I only recognize the question mark bit. I don't know the back end of the lion. Interesting thing though, if I was walking outside and someone pointed up at that bit of sky and said, "What's that?" I wouldn't say the constellation Leo, I'd say Jupiter. Actually, no, I'd get my iPhone out and do the Star Walk thing and then go, "That's Jupiter." So someone didn't check this before writing that in the script.
boyhood fantasy data. I must have seen this ship hundreds of times in the Smithsonian, but I was never able to touch it.
So this is just a silly thing, but since Picard was so excited about this, should have become vice president, right?
Magnetize.
So this is cool. We don't often deal with zero gravity in Star Trek. They just have magic gravity on their ships, and that enables them very conveniently to film in Earth gravity and just have everything work. But in this movie, they actually go outside, so we learn that their magic gravity only works on the interior of the ship. Fine, that makes sense. And so they walk around outside using these magnetized boots, which, fair enough. It's actually pretty similar to what we saw 2 weeks ago with these Velcro shoes. So it's a way of being stuck to the ground in the absence of gravity. Now I will say that in the 30 years that passed between the making of 2001: A Space Odyssey and Star Trek First Contact, they still didn't figure out that being stuck to the ground is not the same as being pulled down. So in neither case do they actually move as though they're in zero gravity. It's almost as though it was actually filmed in a soundstage on Earth. Almost. But the zero gravity in this movie gets weird. So much I don't understand about this scene. So, they have magnetized boots, that's cool. They can walk around and they stay stuck to the ship. But just as a safeguard, wouldn't you want to tether yourself in some way? Because if you happen to lift both feet at the same time, you're kind of screwed. So I did manage to convince myself that Picard pushes off from the ship's hull there when he demagnetizes his boots. Because at first I wasn't sure what was propelling him across the deflector dish there. But assuming he does propel himself, why he starts spinning, I'm not really sure. It kind of looks like he's on a wire, just saying. And then, thank God, he manages to grab the other side, because if he missed or slipped, then he's gone for good. Again, a little bit of rope would have solved an awful lot of problems, but not much investment. So again, nice and dramatic, right? You've got your swelling music, you've got the thing lifting up with all the Magnox coming off, it's cool. But similar to another rant I had 2 weeks ago at 2001: A Space Odyssey, the absence of a downward force is not the same as an upward force. So you can release the magnets that are holding this assembly down. It doesn't mean it's going to start flying up. And it's really unclear to me what was pushing it up, especially when there's a Borg dude trying to push it down. That should have kind of either slowed it or pushed it down, and then he should have gone off flying in the other direction because Newton's laws. Unclear. It's a cool dramatic scene, I guess.
Assimilate this.
So we get a couple of explosions in space in this movie, and so I would be remiss if I didn't point out the massive and repeated movie flaw of sound in space. That should have been a completely silent explosion because they are out there in the vacuum-ish. That sound should not have be able to travel to them at least. So the sound in space is a massive flaw. I get that movie directors think this is how they make the explosions dramatic, although I beg to differ. However, I will give them a pass on this occasion just because Worf saying assimilate this is pretty cool.
Look at that. What, you don't have a moon in the 24th century?
Sure we do.
So I said in the intro that I was going to say that this movie does one thing better than the more serious movies Apollo 13 and 2001: A Space Odyssey, and this little scene is actually it. And it's going back to my repeated rant about the phases of the moon. So a quick refresher for those who haven't been coming to these regularly, this is how phases of the moon work. We've got the Earth, we've got the sun over here lighting up one side of the Earth. The Earth is obviously rotating, but that side is always going to stay lit. It's just going to be a different bit of landmass that's facing the sun. The moon, of course, is orbiting the Earth. The orbit of the moon around the Earth is much slower than a rotation of the Earth. So for a day, you can say that the moon is basically stationary. If the moon happens to be full, so it's way over the other side there, on the opposite side of the Earth from the sun, you can't see it during the day, because on the day you're on this side facing the sun, the moon's way over there. When you get to sunset, you start to see it on the horizon, i.e. it's rising. It will be directly overhead around midnight when you're pointing that way, and then it will set when you get to sunrise. Relevant to this scene, the waning crescent, that's the phase of the moon we just saw, is going to be positioned over here. That means this is the Earth's rotating this way, so this is sunrise. Sometime in the morning, you're going to see a waning crescent. That's when it's directly overhead, rather. And then it will set sometime in the afternoon. They make a big deal of the fact that this launch takes place at 11 o'clock in the morning. And at 11 o'clock, well, it's actually 10 o'clock in the morning at that point because they're an hour before launch, you would indeed see a waning crescent directly overhead, which is where they're pointing. They're about to launch, so they're facing straight up. That's pretty cool, right? I'm willing to bet someone actually put thought into that, which is really, really cool. And it's obvious why they chose that phase of the moon, because they're facing directly upward. They've already set the time of day. That's the phase the moon has to be. Minor quibble. On the 5th of April 2063, we will actually have a waxing crescent, not a waning crescent, so the other side should be lit and it shouldn't be directly overhead. But, you know, baby steps. So I want to finish by getting to the major point of this movie, which is warp drive. Usually when I give talks about the science of Star Trek, I say I'm not going to talk about warp drive and transporter beams because those are things that are just necessary for the plot, even if they make no sense. And then people always ask me about them. So since this movie is about the invention of warp drive, let's talk about it for a moment. So why do we need warp drive? This is because of Einstein's theory of special relativity. A lot of people know that nothing in the universe can move faster than light. But not many people really understand why. They might know that it's because of special relativity. That sounds complicated. It's really not. And so I hope I'm going to convince you that special relativity is really, really straightforward, and that is actually what makes it really cool. So let's take an Enterprise. I'm an original series fan, so this is the original series Enterprise. And let's say we're doing a race, and we're going to travel 100 miles, and we're having a competition to see who goes the fastest. How do you measure speed? Speed is distance over time. So we have our course set up, which is 100 miles long. And we're going to measure the time at which we cross that first line, the start line, and the finish line. We're already going our top speed at this point. We're not going to deal with accelerating. We're already going as fast as we're going to go. We measure the time here. We know the distance. Speed is distance over time. So you calculate your speed, and hopefully you're the fastest and you win your race. But what if Sulu is a little bit drunk, and instead of going in a nice straight line, he veers off to the side a bit? So we're going the same speed, but here we've actually traveled more than 100 miles because we've gone off at an angle. We're still, though, only measuring the times at which we cross the start line and the finish line, so it's going to take longer. So we will measure the speed as being lower. So you travel more distance. In this case, we're moving in another dimension that we don't care about, the y-axis here. Then it appears that you're going slower. Now, the leap you have to make with special relativity is that this axis is time. Time is just the same as distance. You don't have to be able to conceptualize what that means physically, because no one can. Just assume that time is one of your axes of distance. And now when Sulu is sober, we're traveling at a constant speed, all of us traveling at the speed of light through time. And this is assuming we're stationary. And we're basically always stationary because although we move around in space, we're moving so much slower than the speed of light that we're veering off in that distance axis only a teeny tiny little bit. So now when Sulu's drunk, what it means is we're moving appreciably through distance, i.e. a significant fraction of the speed of light. And now, although we're going the same speed overall, the speed you would measure through time is now slower. Therefore, time slows down if you move really fast. And that's just because you're using some of your speed to travel through space instead. So there's a limit. You can stay completely stationary in time and use all of your speed, all of the speed of light to move through distance, and you haven't got any more speed to use. That's as fast as you can go. And that is basically why nothing can move faster than the speed of light. And this is a problem if you want to make a TV show or a movie where people hop around from one planet to the next 1 week after the other, because space is really, really big, and light is actually pretty slow. It takes 8 minutes just to get from the sun to us, and that's, that far. If you want to get to the next star, you're talking about 4.5 years, and that's only to get next door. So, hence, warp drive. So, pretty picture of the Enterprise going at warp. But what is warp drive? It's basically just writers waving their hands and saying we can go faster than light now. They do have a technobabble explanation, which is to do with matter and antimatter. So here's matter. This is a hydrogen atom. It's the simplest atom there is. It has a proton in the middle and an electron spinning around it in the classical picture. So antihydrogen is this antiparticle, so they have opposite charges. Instead of a proton in the middle, you have an antiproton, and instead of an electron, you have a positron. So this is a proton with a negative charge and an electron with a positive charge. If those two happen to collide with each other, they annihilate and produce energy. Now, this is a real thing. It produces a lot of energy, enough energy, maybe, to create warp drive. There's also this dilithium crystal thing, which acts as kind of a catalyst for this reaction. Unclear what dilithium is. In the real world, it will be two lithium atoms. But in one Next Generation episode, they show a periodic table where it has an atomic number of 87, which is actually francium. Unclear. It's a thing. So they're creating all this energy, and what is this energy actually doing? What it's doing is warping space, hence the name warp drive. So if you think of space as being nice and flat, those of you who've ever seen me talk before know it's not always flat, and what we're going to do is bend it. And we do this by compressing the space in front of us and expanding the space behind us, and we call this a warp bubble. Well, we already know that although things cannot move faster than light, you can simulate things moving faster than light by expanding space faster than light. So if you look at very distant galaxies, they actually appear to be moving away from us faster than light. They're not, it's just the space in between is getting bigger. So kind of in physics land, this sort of works. There are real physicists who have kind of postulated that this works mathematically. There's a couple of big problems. First of all, you can never get a signal from your ship to the front of the warp bubble because your signal can only move as fast as light, which means not only can you not turn this warp bubble thing off, you can't turn it on in the first place. So it's really unclear how you control it. But you know what? It's a made-up thing from a TV show, and it lets us visit lots and lots of planets in a short space of time. So it's all good. Now, because I am a little bit of a Trekkie, I do have to end on one very, very nitpicky rant that is very important.
Mr. Cochran, do you have a first name?
Zephram.
Zephram Cochran? Of Alpha Centauri? The discoverer of the space warp?
That's right, Captain. But that's impossible. Zephram Cochran died 150 years ago.
So that dramatic music is really warranted because something spooky is going on here. First of all, Zephram Cochrane in the original series was from Alpha Centauri. This implies that, I guess, at least a generation before he was born, we'd managed to get as far as the next star without warp drive, and then that's where he was born. But somehow he's now from Montana. Also, I don't want to guess how old Zephram Cochrane's supposed to be in First Contact. There is something spooky going on. That clip is from the episode Metamorphosis, which is actually a really good episode. And he does have this weird thing going on where this kind of energy being thing is stopping him from aging. But it's only stopping him getting older, it's not making him younger. So I'm really confused about the timeline of this. However, one thing that does seem pretty consistent is we learned in First Contact that Zephram Cochrane did not discover warp drive alone. He was assisted by a woman who got no credit, so some things never change. And that is where I'm going to end this rant. As we mentioned at the beginning, this is my last talk in Texas before I move. I actually leave this weekend, moving to Australia. So if you do want to keep up with my science rants, you can do so on the internet. I have a blog on Tumblr called Snarky Astronomer, where I'm currently ranting about the original series of Star Trek. I might pick up doing Discovery if it turns out to be good, we'll see. Astronomy on Tap ATX has a YouTube channel where we put all of these talks for people who can't be here. And little side note about what I'm going to be doing in Australia. This is a true story. One of the projects I'm going to be working on is actually this one. I often say astronomers should never be allowed to name anything, but this is actually not a terrible acronym by astronomy standards. It stands for the brightest of reionizing galaxies. It's a real survey with the Hubble Space Telescope and proof that astronomers are nerds. So thank you so much for everyone for coming out tonight, and not just tonight, but for the last year and a half that we've been doing these screenings, and for the last 3 years of Astronomy on Tap. It's been really fun being here in Texas. You have been a great audience. Austin is such a cool, nerdy city. It's been really great to be here. I want to say thank you to the Alamo Drafthouse for hosting these. This has been really fun. To Max for emceeing for me. Lara for doing the filming tonight. Again, all of you for coming out. Steve, who's in the audience, for actually bringing me to Texas in the first place. It's been fun. And hopefully I'll see you all around at some point in the future. I want to wish all the best to any of you who have friends and family on the coast at the moment, and all the best for the future, and live long and prosper.